Hi everyone. Thank you for coming and attending this talk. Today we're going to talk a lot about data caching, but before that, let me quickly thank the XtremePython team for giving me this wonderful opportunity. Let me quickly introduce myself. Hi, I'm Ria and I'm currently working in the fintech industry. Over the course of my career, I've worked with multiple database systems and evaluated different technologies. I think what makes learning even more fun for me is to understand the whys and hows behind all the system design principles, understand the fundamentals, and break down complex topics into easy, understandable bits. I'm also very passionate about organizing outreach initiatives for women in STEM and giving back to the community in whatever way possible. I love to read and also play musical instruments in my free time. So, what should you expect from today's talk? Firstly, we talk a lot about data caching. We learn about caching. I'll share some of my learnings and some important questions that you should consider before caching your data. We see how caching can be implemented in Python while also explore some insights and strategies. And I hope by the end of this presentation, you're not just excited to explore data caching, but are equally enthusiastic to learn more about other system design principles to boost application performance. Let's get started. Starting with the absolute basics. What's a cache? So every one of us has that messy chair in our room which is piled high with clothes. One reason could be that we are too lazy to put these clothes back in the closet, or it's just the convenience to be able to grab whatever we want quickly. I picked up this analogy from this hilarious tweet that compares this messy chair to a cache. A cache, just like this chair, serves as a temporary location for us to be able to quickly access whatever we need, our frequently accessed items like a favorite pair of jeans, without making that trip to the closet. Similarly, in the world of computing, when a user requests for some data, first it checks the cache, like you would have checked your messy chair. If the data is found there, it's returned back to the user quickly. Else, it then fetches, if the data is not found, it then fetches it from the main storage, which could be the disk, like grabbing your clothes from the closet. So caching is this technique to improve the overall response time of your application by storing the data, the frequently accessed data, in a location that is closer to you, that is faster to access. With caching being clear, let's talk about latency. What's latency? In very simple terms, latency is the time it takes to retrieve data that you have requested for. And as developers, everyone should understand these numbers. Maybe the accuracy of these numbers is not the important point over here because that might change as and how technology advances. But the magnitude of difference that it creates as we move down the hierarchy is the important bit. So L1, L2, L3 cache boasts about sub nanosecond latency. And then we have RAM, SSD, SDDs. Accessing something from the random access memory versus accessing something from disk IO has its own set of advantages and trade-offs. Of course, having data in RAM gives you high read-write throughput, lower latency, but the data set cannot be larger than memory. RAM is volatile in nature. You need to move your data to disk in order to be able to persist it if that's your goal. And not everything can be stored in RAM. With these concepts in mind, let's move forward and talk about some key considerations that you should keep in mind before caching your data. Ask yourself these questions. Am I using the cache to mask an underlying issue? So using caching as a band-aid solution to cover up the underlying performance issues is a common pitfall. Like many developers use caching prematurely just to avoid dealing with that problem. That problem could be maybe your database queries are inefficient. You try to query something on your e-commerce website and that's taking a lot of time to load. Have you considered that that might be an issue with improper indexing? Indexing might solve that problem, but putting a cache in front of your application and just caching those results of your database queries could temporarily solve the issue but doesn't handle the fundamental problem. Next could be that you're using the wrong database for your application. Based on your use case, maybe the database that you're using is unsuitable and that is causing the performance issues for you. Surely using a cache would solve the problem temporarily, but that just adds unnecessary overhead and cost to your system. And you might run into these problems again because the database that you have used is unsuitable. For example, maybe for a read heavy application, you're using a traditional relational database system, while moving to a NoSQL one would have been a better choice. Next could be poor data modeling, that maybe your schema is designed in such a way that it is leading to excessive joins between multiple tables, and that is causing performance issues. Putting a cache right there, caching the results of the frequently requested queries would surely solve the problem, but it's not the right thing to do. Fourth one being overlooking code optimization opportunities. Maybe there's an algorithm or an if inefficient code that is taking a long time to execute, but rather than dealing with that, we just cache the results so that whenever somebody requests for that data or triggers the recomputation, we just can give back the result quickly. So we are not really handling the inefficiencies of the code and using caching as a banded solution here. These are just some of the examples. There could be more such issues, but the point here is to not use caching just to mask the actual problems and to understand what is wrong with your application. So when should one use caching? Ask yourself this question. Is the data being frequently accessed? Effective caching hinges on you being able to understand the access patterns of your data by employing proper metrics around that. If the data is being frequently accessed, it makes sense for you to put that in the cache. If it's really being used, having that in the cache is just wastage of space and undermining the benefits of caching. For example, you have a content-based website where multiple users are requesting for the same image. Rather than fetching that from the source, you could cache that. Like on social media platforms, they usually cache user profiles so that they can be easily and quickly retrieved by the users. Another thing to note here is that the data should not be too dynamic. If the data is exhibiting regular changes, for example, you have cached real-time stock prices. Due to the constant fluctuations, they are continuously changing and you might return stale data back to the users. The price has already changed and you are giving the older value to the user. Caching something like that would not make sense. So a suitable candidate for caching would be the one which is frequently requested. Second, output should not change frequently. As we just discussed, storing real-time stock prices won't do you much benefit. But other than that, storing semi-static data like user profiles or product catalogs, of course, would be beneficial as it could improve the response time of your application. Thirdly, should take a long time to execute. If the time it takes to get something from the main source is the same time it takes to fetch something from the cache, caching that data wouldn't really provide you with much benefits. How will you ensure cache consistency? Now, as we discussed that we have pointed this out multiple times that we have limited space, we only want to keep items that are useful, that are being frequently requested, and that would reap us the benefits of caching. Now the space is limited, so to add new data, something needs to move out. And there's a possibility that the data that is present in your cache is not synchronized with the actual source of truth, that is like your main storage or your disk or your database. In that case, you need to refresh your cache. For refreshing your cache, you need to do cache invalidation, that is clearing your cache. There could be three ways: manual, where developers explicitly invalidate the cache themselves, like you clearing your Chrome cache yourself. Event-driven, invalidation in response to a specific event, maybe something in the database change and that is triggering the change in your cache. For example, particular value A changed in the database and now you also want to update that in the cache. Third is time based. That is, I think, the most frequently used one, that you set a time limit after which all the entries in your cache expire and fresh data is fetched from your database, just refreshing the cache. And trust me, this is one of the most hardest problems to deal with when designing systems, that when and what should be your cache invalidation strategy. Moving forward, what caching approach fits our needs? As I discussed multiple times till now, that designing large scale systems is all about keeping the advantages and trade offs in mind. There is no one size fits solution for our applications, and everything is a game of hit and trial and what suits us the best. So maybe data consistency is very important to you. So you might go with the write through strategy, but that would lead to higher latencies than the write around strategy. Choosing what is best for your application is the important bit here, and understanding your use case fully, that what you are ready to let go of, is the important bit. How to implement caching? So I'm going to discuss some easy ways of how you can do that in Python. First is the dictionary. So the code snippet that you see on your screen, in here I am trying to fetch some static data from an API, and you see that this uh, snippet over here becomes a bottleneck, because each time a user would call this function, they would end up fetching or hitting that server endpoint again and again. This can be avoided. How? By using caching. So we make a dictionary, a cache in our application, we initialize it, and the first time the data is requested, we store that data in our cache. Next time, when somebody requests for this function, first it would be checked in the cache. If it exists, it would be returned, else it would be fetched from the main source, what we have discussed till now. So the time you see it takes to execute the actual request of fetching it from the main source is 1.14 seconds, while from the cache it's 0 seconds. Right now it was just one request. As and when the number of requests increases, this time over here, 1.14, would increase as it puts unnecessary load on the server, while caching helps us with that and improves the response time of our application. Next method is decorators. So you could use decorators like the LRU cache. This, you just wrap your code logic with this decorator, and this is the classic Fibonacci example. So the Fibonacci of say number 5 would be the Fibonacci of 4 plus the Fibonacci of 3. This reminds me of my data structures and algorithm days. And if you remember the recursion tree, you would realize that we were doing a lot of recomputations at every step. We were recalculating the result, which could have easily been stored somewhere. That technique was called memoization, the technique of caching functional calls. So over here, you can see that I calculated the Fibonacci of 40, and that took around 21 seconds, while by introducing the LRU cache, it just took 0.0 seconds. It would not always be 0, as in how the number increases, maybe 140, the Fibonacci of 140. This would be more than 0, but extremely less than what it would be without caching. So you see the cache that we have used here is LRU cache. That is the least recently used cache. So what that means is that, for example, the size of your cache, max size, I have set to 5. There are 5 elements right now in your cache. So when the 6th element comes in, one of these items need to move out. The one which will be removed is the least recently used one. That's the cache eviction policy which this particular decorator follows. You could also use least frequently used one, the most recently used one, or first in, first out, depending upon the needs of your application. Moving forward, what we have seen till now are examples of local caching, where the cache is tied to your application. And since it's tied to your application, it is also very limited. It is also limited to the size of the device where your application is running. What if you want to have a different caching layer? So you could use caching as a service. So for example, if you have 2 app servers and each of them have their own local cache, one of them goes down and the local cache is also wiped off with that. So you could like have another cache that is not restricted to your app server. Here you could use Redis or Memcache, and these solutions offer much more than just caching. It could be a single node, or they could span across multiple nodes, forming a cluster called as a distributed cache, which invites its own set of problems and complexities, and that is for another talk. So, this was just an example to tell you how caching can also be used externally. In Python, you could use the Redis client to just import Redis, and that would get you started with the Redis client in Python. And for Memcache, I think the library is PyMemcache. So, moving forward, another thing which I wanted to discuss is measuring cache effectiveness. It is very important to have proper metrics around different parameters like your cache hits, cache misses, the latency, the time it is being taken to fetch something from the cache. Maybe you need to tweak the time to live parameter. The time when somebody requests something from the cache, it is being evicted from the cache. That could be a problem for your application, could lead to performance issues despite having a caching solution in place. So having proper metrics around that is equally important than thinking about the other issues that we have discussed in today's presentation. With this, we come to an end. Thank you so much for attending this talk. I hope this was helpful and like a crash course on data caching. If you have any questions or just want to bond over books, tech, or music, I'm happy to connect. Thank you so much again, and hope you have a wonderful evening ahead.